Oh,
here we go. Okay, welcome everyone to the Astronomical Society of Edinburgh, wherever you are in the world. And our speaker is quite a long way away tonight. And we have people from all over the world joining us on YouTube as well as our board members on Zoom as well here. This is what we've got coming up tonight. I'll just give a brief rundown of what talks we've got lined up over the next few months. And then it's straight on to our main speaker, Emily Lakdawalla, tonight about exploration of Mars. Really looking forward to that. So thank you, Emily, for coming on and doing this for us. It's great. Staying in touch with us, there's lots of ways you can do that. Our website has everything that we're doing on there as well. Facebook, we post lots of information as well, and our Twitter feed. And we've been doing loads and loads of meetings over the last couple of years during the pandemic. So you can see all of those on our YouTube channel. There's quite an amazing array of speakers on there, and worth looking at some of those, all of them actually. This is what we've got coming up. On the 3rd of June, you may have heard about the new observatory in Moffat and the borders of Scotland, so we'll get to talk about that. The important thing for members is it's our AGM, so you'll have had the AGM papers today, so if I can ask you to make a special effort to be at that one, either in person at the Augustine United Church in Edinburgh or on Zoom with us. That's very important so that we can continue to run the society successfully. We have our imaging and observing group on the 8th of June. On the 17th of June, we'll have a talk from Dr. Natalie Starkey about the volcanoes of the solar system. Our meeting in July, we decided to do another members' night again. The last one was successful, although slightly spoiled by the pandemic when I certainly couldn't turn up at it. So we will have short presentations from members at that meeting. On the 15th of July, the Icarus Observatory, if you follow Stargazers Lounge or First Light Optics, they have a remote observatory in Spain, and Grant from First Light Optics will be telling us about that observatory. We have our usual August break. It's not a break from observing, so we'll carry on observing hopefully through that. And then just a few items here that we've got to look forward to: the ground effects of space weather, space art, and the origins of life on Earth and other planets are coming up in the autumn season as well. That's what's coming out. Nigel and his team have been working really hard. We've got an amazing program lined up for the rest of the year and into next year already. So lots to look forward to there. But that's really it from me. So it's over to Emily. So I'll stop sharing. Emily, if I can pass over to you. Are you in LA, something like that at the moment? Is that where you are?
yes, I'm in Los Angeles right now.
Right.
Not quite lunchtime, and lovely weather here. I don't know what you're enjoying up there in Edinburgh, but it's a great day here. So let me get my, oops, hold on a sec. I have to do this in the right order. Share screen. And there we are. Can you see the screen?
Yes, it's coming up now, yeah.
All right, excellent. So let's get started because I have a lot of slides to go through, a lot of stories to tell. So my name is Emily Lakdawalla. I am a freelance science writer, space scientist, space artist, and a lot of other things. And I thought before I get started telling you about what we've learned about Mars in the last 25 years, I'd explain to you a little bit about how one gets to be a professional writer, thinker, speaker, and artist about space. Go back there. Yes. So as you might imagine, this may surprise you, but I was a rather nerdy kid. I was always interested in science. I was, I think, inspired by the first big news events that I can remember are the flybys of Saturn by the twin Voyager spacecraft. There were amazing views of the moons. The eruption of Mount St. Helens in 1981 was huge news. I was like, wow, volcanoes erupt. They happen in our backyard. That's absolutely amazing. And so growing up, I was a big fan of playing with typical engineering toys like Legos and robots like Transformers, and watched a lot of the kinds of public television that we share on either sides of the Atlantic, and was particularly inspired by science communicators like David Attenborough. His show, The Living Planet, I think really ignited my love for geology. James Burke and The Day the Universe Changed was really amazing at storytelling about the history of science and how scientific discoveries they don't just happen. They happen in a political and cultural context, a historical context. That's very interesting. And then Philip Morrison and his series, The Ring of Truth, who just had this very gentle, inquisitive approach to science that I find a little bit lacking in modern TV science communication. And I like to go back to that sense of just being amazed and awed in a quieter way about what goes on in the natural world around us. So I went to college and immediately fell in love with geology as a topic, because I went to college in central Massachusetts, where all of our field sites were out in the wilderness during the leaf changing season. It was absolutely glorious. Person at lower right here is my thesis advisor, Tekla Harms, who was one of the first. There were not very many women in geology before her, and she was a huge mentor and inspiration to me. I became a science teacher for a couple of years after college, where I think I got a lot of experience speaking in front of sometimes difficult crowds. So I highly recommend that to anybody who wants public speaking experience. And while I was a school teacher, this amazing mission began. It was a mission called Pathfinder that landed on Mars on 4th of July, 1997. And its main mission was to land on Mars and demonstrate a new landing technology for Mars. You can see the airbags deflating in these images, but it brought along with it this experimental vehicle named Sojourner. Sojourner was a tiny little rover about the size of a microwave. It was carried on just one of the lander pedals, flattened down on the surface of the lander. And it was purely an experiment. It was not a science mission. It was just, can we operate a rover on the surface of Mars? And of course they could. And so here's a little animation of the rover rolling across the surface. Those were the first wheels ever on Mars back in 1997. And watching that little vehicle tootle around the surface and drive up to rocks and things made me ask the question, can you do geology in space? And of course you can. In fact, this little rover was doing it. And so I went off to grad school to do that. And here's an image from the library at Brown University. Those enormous metal cabinets in the back contained 30 by 40 inch printouts of every photo that the Magellan mission to Venus ever took. And that was what I was working on. These students here are looking at photos from Galileo, which was operating while I was in graduate school. So all these images that you see before you show Europa, a moon of Jupiter, and they were coming down from the spacecraft while I was in grad school. It was a really exciting time, just seeing scientists trying to figure out what the heck was going on. Did all these little scraps of Europa puzzle piece together? Meanwhile, I was working on these beautiful radar images from Venus. And you can see the particular feature that I was studying. There's a little squiggly line that runs down this long valley on Venus named Baltus Vallis. It's actually not very little. The whole thing from beginning to end, it goes way off this picture at either end, is 1,800 kilometers long. And it has virtually no branches. It is probably a lava feature of some kind, but what kind of lava runs for 1,800 kilometers? And that's a question we still don't know the answer to, by the way. And it's one of the reasons that the European Space Agency are launching Envision Venus in a decade or two, in order to, I forget the exact year, I think it's in the 2030s, to go study and try to figure out how there are connections between the atmosphere and the surface of Venus that allow for something like an 1,800 kilometer long river of lava to run across the surface. So the last thing that was operating and that my advisor was working on while I was in grad school was this mission called Mars Global Surveyor. And Mars Global Surveyor is the one that really kicked off this renaissance, this second great age of Mars exploration. And I'll explain to you what I mean by that in just a minute. So once I finished graduate school, I went to work at the Planetary Society, which is a nonprofit organization that advocates for space research and exploration. And I combined my background in studying both Mars and Venus and other worlds, being there for Europa and everything else, with my experience with teaching. And I began to write this new form of communication called a web log, or a blog for short. And I blogged for the Planetary Society for 16 years. And I got to go all kinds of cool places. So up in the Canadian High Arctic at Devon Island, they have a Mars Arctic Research Station. I was there for a different project, but the team who were working on a future Mars astronaut spacesuit said, "Hey, you're the smallest person around. You'd fit in our suit. Put it on." And so it was just the top half of an experimental suit that they were beginning to play with 20 years ago. But it was kind of fun to walk around pretending to be an astronaut on Mars. The next picture shows my first trip to Europe to study for a live event. This was the arrival of Venus Express at Venus. It was also just before the arrival of my first child, as you can see. And in fact, today I am drinking my espresso out of my Venus Express espresso mug that I got at ESOC for that event. I've gotten to cover all kinds of fun things like the landing of the Phoenix on Mars, visited the great gigantic addition at Goldstone. Now I must go visit the ones in Madrid in Australia someday. And eventually I wrote a book on the Curiosity mission. I literally wrote the book on Curiosity. And so I'm actually working on a second book now. This first one is about Curiosity engineering. The second one will be about the science mission. And that's in progress. Currently planning to publish this year, probably will not be until next year, but we'll see how we do. This was shortly after I quit at the Planetary Society during COVID. I have 2 kids and it was all kind of too much to handle. And so I stepped back a little bit from professional career in order to help my kids out and to start a freelance career. This was actually right before COVID, though. This was in February 2020. This is the last public appearance I ever did in person, speaking at Johnson Space Center in front of an IMAX screen. That's the largest screen I think I will ever enjoy the privilege of speaking in front of. It was wonderful. And then COVID happened. And so now I'm doing all my speaking by Zoom. And so I'm very happy to join you all in Edinburgh for this. I think it's fantastic to have the opportunity. I actually love not doing the travel and still getting to talk to people. So here we go. Let's talk about Mars. So to understand the context of the last 25 years of exploration, we actually have to go back quite a bit further than that, to the end of the first great age of Mars exploration, which of course began with the Mariners and continued with the Vikings. There were a few fairly unsuccessful Russian missions in there, but there was one that took some really cool pictures of Phobos, so don't miss those. But anyway, here are some approach images of Mars captured by one of the Viking 1 orbiter. And these are images that it took back in 1976, but they never looked like this to the public in 1976 because this mission happened before modern digital image processing was available. Most of the work that people did with the images returned from Viking was literally printing things out and mosaicing them together, cutting them out, piecing them together to form big maps. Nowadays, I can go into the public archives of space images, pull out the digital data and make these kinds of things with Photoshop. It's all in there in the data. It's just that the original processing capability, even at NASA, was not as great as what I have now on my home computer. And so it's a great pleasure. I encourage everybody who enjoys astronomical imaging to dive into the public archives of space image data from 50 years of space exploration, but only from NASA. European Space Agency has all their archives publicly online as well. And it's very rewarding because you see lots and lots of images that were never released as press release images, because it's like any museum. There's much larger collections than there are on display. And the difference between these data vaults and museums is that you can walk into the collections and go grab any data that you want and play with it. It's a lot of fun and very rewarding. So Viking 1 encountered Mars, orbited Mars, and mapped Mars. And it found a Mars that had a lot of impact craters like the Moon, which implies that Mars has not been very active geologically over its history. But if you look in between the craters, you see some very, very special features. And here is an example of those. These are called valley networks. Unlike the Valtis Vallis feature that I showed you from Venus, which had no branches, this one has a lot of branches. And so that means that the source of these rivers was not a single source. It was all over the landscape. There is a fluid that was flowing downhill and then collecting into larger and larger rivers, streams to rivers, and actually pooling in crater lakes and things. And there was a lot of debate initially about whether this fluid was water or something else, but I think now you'll find very few people who argue that these features were not carved by water. Now, it could have been water. What we don't know is whether the water lasted a long time. Were these rivers like those on Earth that actually flow for a long period? Were they intermittent streams like the kind you have in deserts where they only flow every once in a while when there are storms? Did they flow only under a snowpack or a glacier, an ice pack? We don't know the answers to those questions yet, but those are the kinds of questions that people were asking about these pictures of valley networks. So Mars is really, it's an odd transitional world. It is inactive enough to have preserved craters as old as the craters that we see on the moon, but it's active enough to have had liquid water to have made these kinds of features on its surface. And so the questions that we were left with after Viking, actually, I'm sorry, I'm getting ahead of myself. I wanted to mention the landers. So the Viking landers, there are two of them. They both landed on a Mars surface that is currently extremely inhospitable to life, which was a very big disappointment to the Viking landers because most of their experiments were designed to search for life on the surface. And it turns out that what they found was an environment that contained a lot of really nasty oxidizing chemicals that attack and break down complex organic molecules. Organic molecules, molecules with lots of carbon and other light elements, carbon, nitrogen, oxygen, phosphorus, sulfur. They do best in a neutral or a reducing chemical environment. When there is a lot of oxidizing material around, an acidic environment, it tends to break those big molecules down. So it's not impossible for life to thrive in this kind of environment, but biologists think it's a lot harder for life to get started when you have such an oxidizing environment that is so eager to break apart all of those organic molecules. And so most of the experiments on the Viking landers turned out to produce null results. They did not successfully find life. Doesn't tell you that there isn't or never was life on Mars, just that it wasn't where Viking 2 looked for it. And so at the end of the Viking missions, we had these beautiful global images of Mars from orbit, both in black and white and in color. And we had these experiments that told us that the current environment at the surface of Mars was inhospitable to life. But then we were left with a lot of questions about how was Mars active enough to have water, but not active enough to erase its craters? Is the environment that's there today the same as what it was in the past? We know for fairly certain that the answer to that question has to be no, because the environment today can't sustain liquid water on the surface. So something must have been different in the past. We had all these questions, and then we had no exploration of Mars, this dark couple of decades in Mars exploration after about 1980. So when I was a kid, I got to see outer planets exploration, but no Mars exploration happened until that moment in 1997 when Mars Pathfinder landed. And so there were several attempts to do some Mars missions. There were a couple of really terrible failures, the biggest one being Mars Observer, which arrived in 1993, had a huge suite of instruments on it, and actually just vanished into space 2 days before it was supposed to arrive at Mars. But after that huge failure, NASA and Mars scientists got themselves together and said, okay, we need to organize a way forward to Mars exploration. We need to get this started. We have all these unanswered questions. How are we going to organize the future of Mars exploration? Well, they did that around 4 very specific goals that they agreed upon after a lot of committee meetings. The first one was to determine if life ever arose on Mars. So going a little bit back more in history than the questions the Viking landers were asking, instead of asking if life is there today, this question is a little bit more general than that. Has there ever been life on Mars? The second one is to characterize the present day climate of Mars. In order to, in part, this helps us understand the climate of Earth and the climate of other terrestrial planets. It helps us understand past Earth and present and future as well. Wanted to characterize the geology of Mars, understand the geologic history that led to this modern day enigma of how it is both a place that's been dreadfully inactive for so very long and a place that was active enough to have liquid water. And finally, to prepare for future human exploration of Mars. And what that means is to gather the kind of data and to do the kind of mapping that will help us figure out what questions we should ask, where we should land, whether astronauts can generate whatever they need, like water, especially in situ, what kinds of environmental hazards there are, what the radiation hazards are, that sort of thing. So these are the 4 main exploration goals for NASA's Mars program that have existed since the failure of Mars Observer. And they led to what was publicly described as the follow the water strategy at the end of the last millennium. And so this strategy, follow the water, basically follow the evidence for water on Mars to try to find out what the circumstances were that allowed water to exist. Has there been climate change? Or was this transient geology, or was it something that lasted a long time? Those kinds of questions. This is the sort of unifying strategy for how NASA has been exploring Mars for the last 25 years. ESA, of course, has a different strategy, but they work very closely with NASA. The 2 agencies are incredibly closely united in their work at Mars and everywhere else. And so the European Space Agency strategy is rather similar, with, I think, a bit more emphasis on climate because of Europe's greater emphasis on studying the climate back home in order to understand the future of Earth climate. Okay, so although Mars Pathfinder wasn't technically part of this follow the water strategy, it really did kick things off with here's a beautiful color picture of that rover exploring the surface. And they did they tested out some new methods for studying the surface. They brought the first of what's called an alpha particle X-ray spectrometer to the surface in order to get compositional information. And they also brought the first of these color images to the surface that were quite different from the analog ones that the Vikings used. And digital imaging and the World Wide Web have made Mars, this modern day, or this second great age of Mars exploration, it's been a very online, very digital experience that people around the world could always enjoy because their pictures were always sent straight out to the web. So the same year, this Mars Global Surveyor spacecraft arrived, and Surveyor did exactly what its name says. It surveyed the planet. And there were a couple of kinds of base map information that scientists wanted in order to be able to unify all future data that came from Mars. The main one is topography, and this was the instrument that I had the good fortune to work on while I was in graduate school. It's called MOLA, Mars Orbiter Laser Altimeter. It was an instrument that, as the spacecraft orbited, it zapped the surface with an infrared laser and timed the time it took the laser pulse to get back. And using that information, along with detailed radio tracking data, they eventually produced this global map of Mars's topography. And this was the first truly global view of Mars's topography. Before this, we could get shape from shading like you do with photos on Earth. But this was the first time that we knew what Mars's elevation was all over the planet. And the first thing you want to notice is that Mars is high in the south and low in the north. And because you can see the altitude scale, which unfortunately is not very colorblind friendly, but I can tell you that on the left side, we have the mountains of the Tharsis Montes and Olympus Mons. Mars is very high elevation in that area. On the bottom half of Mars, you have these ancient, high-standing, heavily cratered terrains with a huge Hellas Basin there in the south, the deepest hole on Mars. And then you have, in the north, these much smoother, much lower standing plains. And they're also much younger, as you can tell, because they don't have nearly as many craters. And one thing any scientist who knows about groundwater can tell you is that if you have water flowing anywhere, it goes from high places to low places. So we can tell you instantly from looking at this map that if there's water on Mars, it's flowing not just on the surface, but also under the surface from south to north. And so if there's a water cycle on Mars, if there maybe was an ocean in the past, the jury's still out whether Mars actually had an ocean in its northern lowlands, but water would pool there. It would participate in the water cycle by evaporating up into the sky, and global circulation would bring it back down to rain in the south and run south to north and empty into the northern lowlands. So that was a big deal on MOLA when we got these first maps. And we're like, whoa, look at this huge global topography dichotomy between the south and the north. That's weird. It's very strange. And this is just another view of the same thing. Okay, so Mars Global Surveyor had a couple of other instruments, and one of them was called the Thermal Emission Spectrometer. And the Thermal Emission Spectrometer looks at different wavelengths of light emitted as heat by the rocks on the surface of Mars. So it doesn't care whether it's day or night. It can see this heat. Of course, things do cool off at night, but this is from at this long wavelength. This is just from the internal heat of Mars primarily. And so you can slice and dice the spectrum that gets reflected in order to look for little wiggles, little dips in the spectrum that are indicative of the presence of certain minerals. And the one that this map is showing you is something called pyroxene, which is a mineral found in basalt, the dark volcanic rock that covers a lot of Mars. It covers the moon. It covers our ocean floors. And so this map just shows you that there's basaltic rock on Mars, especially in places that are fairly well scoured by wind, so they're not very dusty. So this map is no surprise. The surprising map was this one that shows you where a mineral called hematite is present on Mars. Hematite is an oxidized form of iron, and it forms in watery environments. There's a few different ways you can make hematite, but they all require water. And I don't know if you can see on your screen through the broadcast, but there's really only one big spot of it in all of Mars. And it's right here at longitude 0, latitude 0, or just a bit off from that, in a place called Meridiani Planum. And so this was a beacon from Mars that said, look here for evidence of past water on Mars. And so when they sent the first actual science rover missions to Mars, they did just that. They sent Opportunity to go investigate this spot called Meridiani Planum, where they'd seen that signal of the mineral hematite from space. Opportunity landed in January of 2004. I was I was at JPL with the science team watching this land because I was working on an education project with a bunch of students who got to be inside mission operations. And when we got this very first picture from Mars, the mast of the rover hasn't even lifted yet. So it's sitting here like it's scoping down its own mast, looking at this is the very first picture it took. And you could see layered bedrock in the near distance. There were scientists who were jumping up and down yelling about the bedrock. There's one named Matt Gollenbeck, who was a landing site selection chair, who was just jumping up and running around circles around mission operations. He was so incredibly excited about this rock. And that was the first thing that they went to investigate. Geologists are a little weird about rocks. And so they went up to this one right in the wall of the crater. And we saw these very, very, very thin laminations. And then embedded inside all of those very thinly laminated rocks were these dark colored round things. Each of those dark colored round bits is about 2 to 4 millimeters across. And they looked just like blueberries in a muffin. So scientists called them blueberries. And it turned out, after further investigation and putting their instruments on the rock and finding concentrations of blueberries, the hematite that we were seeing from space is concentrated in these blueberries. And so how does that happen in a rock? Well, this is a kind of thing that we're finding out across all of Mars land investigations that's very important in Mars's history, which is that no matter what kind of rock you start with, after whatever it is has turned to rock, then there is groundwater flowing through the rock that is dissolving materials from one place and carrying them somewhere else and depositing them in various kinds of features. And these things are called concretions. They are little concretions of hematite. So that means there is a little tiny speck, a nucleus, and hematite mineral crystallized around that nucleating speck until you form these little blueberry concretions. And so this is a result of lots of groundwater flowing through these rocks for a long period of time after they were buried. And the rocks, as they figured out, were not actually, even though they're very thinly layered, these were not laid down in a lake. After more of the mission exploring others of features across Meridiani Planum, they decided that most of what you can see here are layers of wind-blown sand that were deposited and then buried and turned to rock. And so probably the material that formed these layers was originally laid down in some kind of watery environment. It's a sulfate-rich sand. So it's made of calcium sulfate, which is a mineral that it's gypsum. Okay, it's that white mineral. If you've ever seen pictures of White Sands, New Mexico, that's the material that White Sands, New Mexico is made of. And so this was wind-blown sand that was eroded from one spot, blown in vast dunes across a very dry desert, and then buried and lithified. So the rocks were originally formed in a pretty dry environment, but after they formed, they were full of water. Now, this wasn't an environment that was very good for life. Again, we have this problem of an oxidizing acidic environment. If you put a sulfate mineral, let's try to remember your high school chemistry. If you put a sulfate mineral in water, it dissolves really quickly and you get a very acidic material. You get like sulfuric acid, basically, is what's present in solution. It's nasty stuff. It is very low pH. It will dissolve any organic materials that contact it. So this is not the life-friendly environment we were looking for, but it is strong evidence that there was a lot of liquid water doing interesting things chemically flowing around the surface. So that at least was a first step in that story. Opportunity's twin, Spirit, went to visit a rather different kind of environment. It's a place called Gusev Crater, which this is the crater right here, Gusev. And as you can see, there's a valley entering into it. Now, if you remember what I said earlier in this conversation about valleys that branch and valleys that don't branch, you can see that this one doesn't branch. So that means that it was a different kind of environment from those valley networks. This one had a source, a single source. So there were, later in Mars's history, there were events called outflow channels, where some triggering event released a huge flood of water all at once. Maybe a volcanic eruption or an asteroid impact penetrated through the frozen surface to a groundwater table or something like that, or melted a bunch of existing ice and caused a big flood suddenly to go from one source downhill until it ended and then it stopped. And that's the kind of event that forms this kind of channel with no branches or virtually no branches. And so there was evidence from orbit, from these pictures, that we know the Gusev was once filled with water. Now, the floor is very, very, very flat now, and there's lots of evidence for volcanism. This is the flank of a volcano up here called Elysium Mons. And so the floor could be flat because it's covered with volcanic lava. But we know that at one point it was filled with water, so it was another good place to go. It was also very flat and safe to land, so they sent Spirit there. This was Spirit's first picture from the surface of Mars. Not nearly as fun geologically as the one we saw from Opportunity. Good thing we saw Spirit's first, so we weren't disappointed. All the rocks they could see were basalt. They went to an impact crater hoping to find the kind of great rocks that Opportunity had seen. They didn't see any of those lovely sedimentary rocks. It was called a basalt prison by the science team. There was nothing but volcanic rock. It was kind of miserable. And so it was beginning to look like they were going to fail at following the water. But they were like, well, one thing we can try is we can go to a high place that may have been above all of the lava flowing into this crater. And so maybe the rocks in Dembar Hills will have signs of the ancient environment that existed in this crater before it got flooded by lava. So they drove. They weren't sure if they were even going to make it to the hills, but they figured it was worth a try because nothing around here was worth looking at. They got there on Sol 170, which was already 80 sols, 80 Martian days past the rover's warranty. And they came across this rock they called Pot of Gold because it was the pot of gold at the end of the rainbow. They investigated it and they found very similar chemistry to what Opportunity had seen on the opposite side of Mars. They saw evidence for rocks that had been soaked wet with groundwater containing lots of acidic minerals. And now this rock has this very strange appearance because the groundwater experience softened its minerals. It's made of softer minerals than it was before. And now the windy, modern, dry environment has sandblasted it and has left more erosion-resistant nodules sticking up on sticks that look like crab eyes or something. It's a very bizarre-looking rock. And it turns out that Spirit lasted 10 times that long, more than 10 times that long. It developed some mobility problems with age, as we all do, and it was dragging one of its wheels when it passed through this area of relatively innocuous looking dirt and scraped up incredibly bright white material that turned out to be almost pure silica. And this kind of silica forms in fumarole environments, which is to say it's a hot spring. It's a place where there's volcanic activity feeding water, superheating water, helping it dissolve minerals from rocks and depositing this pure quartz silica. So Spirit did eventually find evidence for past water on Mars in a very different kind of environment from the one that Opportunity had found. So this is a hot spring environment. And if you've ever visited a place like Yellowstone National Park, I know there are equivalents in Europe, but I'm not exactly sure where. But those kinds of environments have a lot of microbial activity. And so this is one of the reasons that astrobiologists get so excited about animals called extremophiles, the kinds of animals that can live in these nasty, hot, volcanic, sulfurous environments. They would have thrived in this ancient Martian environment. Maybe not originated, but they would have thrived there. So there have been a whole lot of missions since those two. Europe's Mars Express has done some really impressive work mapping the mineralogy of the surface. So this is the instrument Omega on Mars Express, which is still operating, producing a very similar pyroxene map to the one that we saw from Mars Global Surveyor. But the advantage to Omega is that, first of all, it can do imaging in a much shorter infrared wavelength that is much more sensitive to the presence of water within minerals. So it looks for water-rich minerals like clay minerals, and all of the green dots on this map of Mars are places where Omega saw clay minerals in very small spots. And it seems to find clay minerals only in Mars's most ancient rocks, which might tell you about when water was active on Mars. I put a yellow circle here around a very special spot. This is the one of the deepest holes on Mars, a place called Gale crater, which we will come to again in the future. Shortly after Mars Express arrived, Mars Reconnaissance Orbiter arrived, and this is NASA's workhorse for imaging the surface of Mars in incredibly high resolution. So here's a view inside Gale crater from the high-rise camera, and we actually can see the reason that I picked this place out. It's because it's where Curiosity landed in 2012, and that's a photo of Curiosity sitting on the surface of Mars. You can see so you can see the rover here in the center of the dot. You can see the white surface of the deck of the rover, and you can see this darkened area where the landing rockets blew away the bright dust, exposing more of the darker bedrock beneath them when it landed. And so the first place Curiosity headed was this place that HiRISE saw from space, where there is lots and lots of bedrock visible. You can see the layering from space. They knew it was going to be beautiful. Here's the landing site. Landing site, not so interesting, just a bunch of dust and pebbles. You can see, though, that there's where the landing jets blew rocks and dust away, there were signs of what looked like much coarser rock material in those spots. But they didn't stick around. They headed for that interesting looking bedrock. Along the way, they found what looks exactly like the broken concrete in the sidewalks on the way to LAX. You can see it has a smooth surface, and then when you look at the broken slabs of the rock, you can see, how buried in the rock there are these roundish, not totally round, but roundish cobbles. Anybody who's ever taken a geology class can tell you that there's only one way you make round rocks, and that's by tumbling them in a stream. And so this rock, which Curiosity saw very early on in its surface mission, was instant evidence for a stream flowing across the surface of Mars for the first time. This is a conglomerate rock. The pebbles and gravel in it are not terribly well sorted, telling you that this hasn't flowed very far from where it started, so it probably just came right down off the crater rim. And the size of the cobbles tells you how much water had to be flowing. So we know that the river that deposited this material was about ankle to hip deep when it was carrying these rocks along. So they drove along. The pictures were instantly lovely. No matter where you drive in Gale crater, you always have beautiful views of distant hills as well. And here is that second spot that I circled in yellow on the HiRISE image. You can see layer after layer of rocks. This is just a geologist's wonderland. There's nothing but bedrock as far as the eye can see. And Curiosity has had a fabulous mission to Gale crater since then. Basically, what you see down here is the very lowest stratum in all of the rocks that Curiosity has explored. And throughout its entire mission, it's basically been driving uphill, first toward the central mountain of Gale crater and then up it. And as it drives uphill, it drives through stratigraphy. And so we know from the law of superposition that whatever's at the bottom is the oldest, and whatever is on top of that is the next oldest, and so on. So Curiosity has been reading the history of the activity inside Gale crater ever since it landed, just by driving up the rocks. And so they got down to business. They were able to do proper geology. They've been naming things for places all over the world. There's naming themes to each little region. And so there is one later on in the mission on a place called Vera Rubin Ridge that's named for spots in Scotland. And so, of course, I mostly recognize the names of all my favorite whiskeys and all of the sites that they visited, but definitely look those up, because if there's a whiskey, there's probably now a target on Mars named for the town where it's made. And so this is a close-up image of this Gillespie Lake sandstone. And so we see here, again, it's a rock that is formed from broken bits of other rock. That tells you it's a sedimentary rock. It was made from other bits of rock that were broken up and then cemented together. And again, we have slightly rounded, larger pebbles embedded inside a finer matrix, except in this case, the scale is much, much, much smaller. We're dealing with something called the Mars hand lens imager. It's like a geologist's hand lens, the little thing they hold to their eye to look down at the rock. And the biggest little pebbles that you see here are only a couple of millimeters across. So this is very, very fine scale. Those are big enough that they are too big to have been carried by wind. So we are still looking at a water-carried sediment, but it's finer grained, which tells you that the water was flowing more slowly. And it's also better sorted, which means that it was flowing farther from its source. It flowed a longer distance before it was deposited here. So we have a change in kind of environment. The stuff we saw before was from a more active environment. This is from a less active environment. Curiosity has a drill. And the first thing we found out with the drill is that Mars is red on the outside and gray on the inside. And this is actually very good news if you're looking for ancient life, because red is oxidizing, that's rust. That's an environment that attacks organic chemicals. Gray is a sign of reduced chemistry. So this oxidizing chemistry that characterizes modern day Mars and makes it rusty and red is only a surface coating. The ancient rocks that tell us about Mars's history are actually from a reducing environment, at least in this spot. And so we're looking here at a very, very fine-grained rock. In fact, its grains are so fine that Mars hand lens imager couldn't see the individual grains. It does see some nodules here. So these little specks are other nodules. They're more concretions. They're not hematite. They're a different mineral. But the actual mineral that is laid down in these rocks, it's clay. It's a very, very, very fine-grained sediment. And a clay, fine-grained sediment tells you that you were in a lake when this material was deposited. So we have here signs of an ancient lake on Mars that had a reducing or neutral pH environment, which is exactly what the mission was sent there to look for, to find places where life could have originated and thrived on Mars. So here we are. Here's evidence for that in the very first place that Curiosity drilled, which is very exciting. And so after that, Curiosity has been on this amazing road trip for very nearly 10 years now. Because it has this hand lens imager on the end of its arm, it can take selfies. And so that's how we get these images. It's not quite like the selfie that you take. It's like having the problem is that the camera has a very narrow field of view. So it can't take a single image selfie. It has to take these vast mosaics, so about 50 images, and then it puts them together. But they coded it so that the camera moves around its optical axis. And so all the images for these selfies are taken from the exact same position in space optically. And so they're very easy to mosaic into these beautiful mosaics. Here, Curiosity is looking at a spot again where it just drilled, and you can see the gray spot here. It's very small, you might not be able to see it. But this is at a spot called the Kimberley, where they found, again, more evidence for a different type of water activity. The Kimberley was evidence for a stream emptying into a lake. This is a delta environment. And so we've seen lots of different kinds of lake-related environments. We've also seen lots of different chemistry. You can see that the rock that they drilled here is a lot darker. So that implies that there are different minerals present. The mineralogy changes depending on the source material, but it also depends on the environment. It depends on what the water activity was in these rocks after they formed. And so now I'm just showing you pretty pictures because gosh, these pictures are pretty. And so here we see a lot of cross beds. And these are very large crossbed sets. So some of them, while they may have formed in a water environment, it's also just as likely that these formed in a windy environment, an aeolian environment, just like what Opportunity saw. Here's a view showing two drill sites in a place that had a lot of silica, which was very unusual. And so they've seen signs of the kind of fumarole activity, not nearby, but that generated the kinds of chemistry that has altered the chemistry of these rocks in the past. So not only were they wet when they formed, it was an environment where life could exist when it formed, but there have been many subsequent periods when these rocks were completely soaked with water and you could have had life thriving there. Unfortunately, Curiosity has no capability to detect fossils at micro scale. It would have to be a dinosaur bone for Curiosity to be able to find it. And nobody seriously expects dinosaur bones to be found on Mars. So we'll need future missions to be able to tell if there was microbial life in these environments. But we know now that the environments existed that could have supported life on Mars. Again, pretty pictures. These are some modern active sand dunes that are made of basalt sand. So they're much darker than the dusty rocks around them, and you can actually see them moving from space. And Curiosity does a lot of long distance imaging to see how the shapes of the ripples in the sand dunes change. Here's the front, the Stoss side of one of those sand dunes, and you can see where sand slips down. Curiosity saw changes in these dunes while it was sitting there, and in fact doesn't like being there with its hand lens imager, because if you put the hand lens imager up close to one of these things and then you open the lens, then you've got sand blasting your fancy lens, and you'd rather not do that. And so they keep the lens closed most of the time when they have a transparent lens cover, but it's very dusty. So the images are not nearly as good, but they get you at least what you want to see when you're looking at the up close. So here's a picture from Vera Rubin Ridge, which was a really important target for the mission that they identified from space. Vera Rubin Ridge showed signs of hematite, just like at Opportunity's landing site. But Curiosity got there and found it to be for a completely different reason. There are no blueberries here, nothing like the hematite concretions. Instead, it looks like there was yet a different period of wetness with water originating from a different direction, possibly from above. Maybe it leached out some materials from a rock layer that used to be sitting above this one that caused the chemical change in the rock from a reduced form of iron to an oxidized form of iron. And so reduced iron is soluble in water, and it forms these dark or these gray rocks. Oxidized iron, the red stuff, the rust, precipitates immediately, and so you get a much redder rock. And so when you get chemistry happening inside a rock that changes reduced iron to oxidized iron, then all of a sudden you get a lot of hematite forming in the rock, and that's what Curiosity seems to have found there. Another thing that it found was that the cement that formed, this hematite-rich cement, is incredibly hard, and they had a terrible time drilling into it. It was really, really difficult, and they made so many attempts that if you look at the map of this phase of the mission, it's like the rover is driving all over the place trying to find a spot it can drill. So to review what they've done with this last 25 years of Mars exploration, what have they accomplished? Well, they have not answered the question about whether life ever arose on Mars. That is still absolutely open to interpretation. But we have done a bang-up job characterizing the climate of Mars, past and present. We've learned a lot about how much of its atmosphere is lost. We've characterized the geology of Mars from space with dozens of instruments, and have done it in a few special landed locations. And we've begun the process of preparing for human exploration of Mars. We've learned some important things about the surface environment, some rather unpleasant things about the presence of perchlorate in all of the rocks. It's an ion that it's pretty toxic. Now, of course, it's also very easy to filter. So it's not a definite. There are people who write about, oh, there's perchlorate in the rocks. Astronauts could never drink the water. It's not true. You can get it out of the water, but it is a complication. It likes to attack organic materials. It makes it complicated to try to look for present or past life on Mars, because anything near the surface that has that contact with this oxidizing environment is going to be attacked by these perchlorate minerals, by hydrogen peroxide that apparently forms when dust devils whip up the dust and cause it to rub statically against each other. So there's all kinds of reasons that the surface environment of Mars right now is exceedingly nasty. But at least we're learning about those things before we send any people there. So Curiosity was really the culmination of this follow the water strategy. We followed the water, we've answered the question, could life have thrived on Mars? Yes, Earth-like life could have thrived on Mars. We just don't know whether it started there or ever existed, much less do we know whether it exists today. So that's clearly the next step. Perseverance, oh my gosh, I didn't change the title of that slide. Perseverance rover has landed last year and is already drilling and capturing samples for a future sample return. This is going to be a fantastic ESA-NASA collaboration. It will require 3 phases with an ESA-like rover like ExoMars, which we had hoped would launch this year. It does no longer looks like it's going to launch this year because of certain bad actions in the Ukraine. But Tom Zurbuchen, who is the head of NASA Science, just said yesterday, he in several tweets mentioned to the public that NASA is now discussing additional support for ESA's ExoMars mission. And one of the motivating reasons for doing that is because we need ESA to be good at rovers on Mars in order for ESA to be able to fulfill their role in the upcoming Mars sample return mission, which involves an ESA-built fetch rover retrieving the samples dropped by Perseverance, a NASA-built lander launching those samples into Mars orbit, an ESA-built orbiter picking up those samples and delivering and putting them inside a NASA-built sample return capsule, and then ESA will deliver the sample return capsule back to Earth, and then the sample return capsule will land. So this is a very ambitious mission. It's like 2 flagship missions. It's going to take a while for it to be accomplished, but after many decades and decades of just talking about it, it's finally actually happening. We're gathering the samples, and we are now in the middle of the collaboration between NASA and ESA to get this whole thing going. And that is what we need to do. We need samples back on Earth in order to be able to answer the next questions, because as powerful a rover as Curiosity is compared to its predecessors, it's nothing like having the full power of a globe full of scientists, amazing laboratories to bring to bear on the samples that we can bring back from space. So that's really the next thing for Mars. So with that, I'll thank you for your attention, and we'll welcome any questions you may have.
Thank you for that, Emily. Before we move on to questions, can we thank Emily for her amazing talk? Thank you very much. If you're on Zoom and you have questions, can you put them in the chat, and Peter will pick them up. If you're on YouTube, can you put them in the chat there as well? Apologies to our YouTube viewers. We got spammed by some nasty people, but hopefully we got them quickly enough. You didn't see too much of that. We have about 140 people from around the world watching you talk here, from the USA to India and all over the UK as well. So Peter, have you got questions?
Yes, we've got a few questions. I had one first, if that could be cheeky enough. And that is, where does Elon fit into the plans?
Well, that's an interesting question. He certainly doesn't fit into NASA or ESA's plans for science. So you'll find if you talk to me for very long about human exploration of Mars that I have a rather edge opinion that I'd rather not see humans walk on the surface anytime soon. And my reasoning for that is because if Mars is a place where there is or ever was life, then bringing Earth life to it in the form of humans and all of the microbes that ride along on us, in us, come out of us, and ride on all of our equipment is going to make it much more difficult for us to find, detect either present day or past life on Mars. And so I promote something that's a little bit different. I still like human exploration of Mars very much. I personally consider rover exploration of Mars to be human exploration, but I understand people's problem with the fact that it takes so much effort just to get the rover to do anything on the surface. And it's nothing at all like having an astronaut with their brain and their dexterity moving across the surface. And so there is a middle way. The middle way is to have humans in orbit at Mars so that there is no time lag in communications between orbit and the surface. And then humans can joystick, they can drive, they can virtually have the experience of exploring Mars through the eyes and other senses of robots. If we can do surgery virtually, which surgeons can now do remote surgery, then we can definitely do geology on the surface using similar technology. And that, I think, would be the best of both worlds, because it's very difficult to land the mass that you need to have humans on Mars. It's very difficult to help them survive on the surface. It's still extremely challenging to do it in orbit, but there are many fewer engineering problems to solve. And I think it is the right way to go for the near future of human exploration. And I would call that human exploration. There are some who would disagree with me, such as Mr. Musk, who would like to retire on Mars, as he's been known to say. I will say, SpaceX builds an amazing rocket. Falcon 9 is the bomb. I stop everything to watch those rockets land. It is the greatest thing ever. So, but yes, keep your filthy human bacteria off my planet that might have life in it, please, for just a little while longer, long enough for us to answer those questions about whether life ever originated there.
Okay, thanks very much for that, Emily. Ian, I think you're first on the list.
It's been my hope that one day a rover will encounter some seashells, and sulfuric acid notwithstanding, what is the chance?
So that's an interesting question, because seashells are made of calcium carbonate, calcite. And carbonate is a mineral that scientists have been expecting to find on Mars since they sent their first spectrometer. Since those thermal emission it was actually the Soviets who first sent thermal emission spectrometers to Mars, and they returned the first of this kind of data. And it was surprising then, and it's surprising now how little carbonate you see on the surface. Because you expect it to be there because Mars has a carbon dioxide rich atmosphere. And so you expect that if there was water on Mars and it had a carbon dioxide atmosphere, then the chemistry would happen to make carbonate minerals like calcite or rhodochrosite or any of these other calcium containing minerals, carbonate containing minerals. And the answer to why we don't see it appears to be the existence of a period in Mars's history when you had a lot of sulfuric acid rain in a highly volcanic environment, spewing out lots of sulfurous gases that combine with the water in the air to make these highly acidic environments. And so we don't see carbonates, we see different minerals, but the carbonates, if they ever formed, and we have seen some now, there are a few very isolated places where there are carbonate minerals. But a lot of them would have been destroyed during this age of Mars that happened in between the past clement watery environment and the present day cold desert. There is this period of volcanic activity and acid rain that probably wouldn't have been very nice to live through.
Thank you.
Thanks for that, Emily. Nigel?
Thank you very much, Emily, for an absolutely fascinating talk. That was wonderful, especially some of those images were tremendous. I just wanted to ask if a site with a due nod to what you've just said about human exploration on Mars, but has NASA been looking at ideal sites for the first human settlement on Mars, and what would characterize an ideal site for a human settlement?
Well, they certainly have. They have since the beginning of the Mars exploration program, and HiRISE specifically, which is the camera on Mars Reconnaissance Orbiter, was designed to look for landing sites for any kind of mission, including human exploration, also robotic exploration. But its camera can get 25 centimeter resolution on the surface. So that's an astronaut foot, basically, if you think about it. So that's plenty of detail to make your hiking maps. And the kinds of things that they're looking for is first a safe landing site. And that involves things like the elevate, is it flat for long enough for your landing radar to figure out where the surface is? You want the wind environment to be safe. If it's too windy, it could blow you off course. So that's where the modern day climate models are extremely important, so you can understand the dynamics of spacecraft entering the atmosphere. You also want to know what resources are available. There are lots of people working on in situ resource development. For humans, the most important resource is water. One of the things we've learned from a mission I didn't even mention, which was Mars Odyssey. My apologies to anybody involved in Mars Odyssey if I didn't mention. I didn't mean to overlook you. Is that they have an instrument that discovered water is everywhere on Mars, just beneath the surface. And so you guys are astronomers, or y'all are astronomers. You know that there are water ice polar caps. And those you can imagine as the water table peeking up out of the ground. So if you go just equatorward of the polar caps, you only have to dig a few inches and then you will get to ice. The far closer you go to the equator, the deeper you have to dig. And so you want to land humans in a place where there is water ice close enough to the surface to have to do very little digging in order to get to that water. And so the answer turns out to be this band in the near equator but northern latitudes. And the reason northern latitudes is because elevations are lower in the north than they are in the south. And so water is more stable closer to the surface in the north than it is in the south, because the atmospheric pressure is higher in the north at the surface than it is in the south. And so wherever humans do land, and for whatever reason, whether it be to try to, I don't know what the reason cited will be. For some people, it's just curiosity. For other people, it's for science. And, we'll see what happens when it happens. For some people, it's a stunt. But the point is that you need, for your mission, you need resources, and if it's science, you need a specific type of target. You need to be answering scientific questions. And that also dictates the landing site choice. One of the exciting things about being able to watch the Curiosity landing site selection process was that was the first time in Mars exploration history when a landed mission got to select its landing site based on scientific criteria, not only safety criteria. And the difference was that Curiosity's landing technology was advanced enough to make its landing region small enough that you could fit that landing region in lots of places that would previously have been too tight to fit a lander. So Gusev crater was the only crater all over Mars that the Spirit and Opportunity landing system could safely land in. But Gale crater was one of several that Curiosity could have landed in. And they landed in it because it was practically the deepest hole on Mars and had good signs that there are many different kinds of geologic activity in the past.
Absolutely fascinating. Thank you.
Thanks very much for that. John Holden.
Hi, Emily. Can you tell us anything about seismic monitoring on Mars?
Yes, so there's a mission sent to Mars to do just that, called InSight. It is now beginning to be at the end of its mission. InSight has two instruments. One of them is a French-built seismometer. The other one is this American-built penetrator. Unfortunately, the second one, the instrument was not able to get itself down into the surface. And that's an example of the kind of thing that we need to know about before we send people. That we didn't understand the way Martian surface materials worked well enough to design an instrument that worked to bury itself inside them. So while that was bad news for this instrument, bad news for this mission, and actually bad news for human exploration, at least we didn't discover that with humans, right? So we need to make these kinds of discoveries with much less risky missions. And so InSight's other instrument is this one seismometer that has been sitting on the surface for a couple of years. I've lost track of time because COVID. But they've been monitoring for Marsquakes, and very small Marsquakes. It's not the kinds of earthquakes that we think about on Earth that have the whole Earth ringing like a bell. They're mostly very small. They're mostly generated near the surface on faults that are still have some slip activity because Mars is shrinking as it cools. All the terrestrial planets do that, and so the shrinking activity causes these wrinkles and these crevices to form, as it does to all of us, I think. And then you also have the occasional meteor impact that makes a pound on the surface, which is a nice sharp pulse for them to detect. And just 2 weeks ago, if you Google for this, they detected their biggest Marsquake ever, a magnitude 5 on the Richter scale. And so those quakes allow them to probe the interior of the planet to answer questions like, where are the interior layers located? We know Mars is layered because we know how dense it is. And its density tells us what its composition has to be. So much metal, so much rock, or at least it gives us sort of an envelope. And so we know it has a metal core. And one of the questions that InSight was seeking to answer is that metal core still partially liquid like it would have been when it formed and like Earth's, or has it solidified? And I believe the evidence is currently pointing toward it's got a liquid outer core, which makes it even more interesting that Mars has lost its magnetic field, because as far as we know, our magnetic field is generated in our liquid outer core. So there's still a lot of questions, but InSight is the first seismometer. You can do seismometry with a single instrument, but it's not nearly as easy or as effective as it would be with multiple instruments. So I do hope in the future to see a mission with many smaller landers that may have less sensitive instruments than the one that CNES built for InSight. But if you have a network of them, then you would be able to do much better at this kind of global seismometry, seeing the interior layering of the planet. So I hope that's in the cards for the future.
Thank you very much. Thank you.
You're welcome.
Thank you for that. Gillian, you have a question?
Yes, thanks very much for your talk, Emily. Having modelled geological structures on Earth, it was really nice to see them on Mars. What I was wondering is, can you date sites where there's been free water on the surface?
Yes, so there is not yet any kind of in situ geochronology for Mars. So there has been no dedicated instrument to geochronology, although there are people working very hard to design such things. And I invite you to look up the name Barbara Cohen. She is a geologist who has done a lot of work in trying to develop in situ geochronology. However, Curiosity does have a gas chromatograph mass spectrometer. And it has the ability to detect argon isotopes. So these are isotopes, they're atoms of argon that have different numbers of neutrons. And a certain flavor of these different number neutron argon atoms are made only by the decay of a different element. Potassium, that's right, it's potassium. And this decay process happens slowly. So it's a kind of clock that you can use to say how old the rocks are. And so they tried that on that first rock they drilled, the one that I showed you with Mars was red on the outside and gray on the inside. And that one, the rock, you have to understand, this was not terribly accurate dating, but they found its age to be approximately 4 billion years. Which, if you know anything about age dating, if you have a problem with your analysis, you get a date that's too young. Okay, so if the analysis failed in some way, you would have gotten a date that was, whatever it was, it would be too young. But the thing is, the whole age of the solar system is only 4.5 billion years. So the fact that we got this age on this rock of about 4 billion years, give or take 500 million, it's not very exact, but it does tell you that we're dealing with extremely ancient rocks here.
Thanks.
You're welcome.
Thank you for that. That's the questions off the chat line. Mark, if you want to move over to Will.
Will, it's over to you. Have you got questions on YouTube?
Yep, excellent talk, Emily. I think everybody's really enjoyed it on YouTube. We've got one question here from Jason Gilchrist. He basically asks, how limited in our understanding of space geology are we by our restriction to interpreting it based on planet Earth geology?
Oh, that's a very interesting question. So I will say the limitation is it's basically what you say. So although it's not exactly how you say it. So on Earth, of course, we can walk nearly everywhere that there is a continental rock environment. However, it's actually very hard to explore the majority of our planet, which is all buried under deep ocean. And so while it's a lot easier to explore small structures and everything in situ, we actually can't get up close or even see from space the majority of our planet. So one of the reasons we go to study Mars and the Moon and other places in the solar system is to be able to see the kind of geology that we actually can't see on our own planet, because we can't see directly what's happening at the ocean floor, except through the cameras on tiny submersibles that just go peek at one spot and come back up. So we are very limited. I'm not going to lie to you. We are very limited in the very limited amount of data we can get back from space. It's expensive to send these missions. It's very far away. We can only communicate with those giant radio dishes, like the one I showed the picture of at the beginning of this presentation. And so our limitations are primarily on the quantity of data and how close we can get to the planet. And the other major limitation is that we don't get the cross-sectional view for the most part. We only see it from the surface. And so trying to interpret those overlapping relationships from space is usually very hard. And so we rely on these surface missions in order to be able to go see it from the side, to be able to drill into the inside and see things in cross-section. Curiosity is the first mission that not only has been able to climb up stratigraphy, but has also wandered parallel along stratigraphy. So you can see how the same layer changes as you go from one place to another within the layer. They did a lot of that on Vera Rubin Ridge. So that's a great spot to look for that kind of results. So I don't think that studying Earth geology is a limitation to what we study in space. In fact, it's necessary to inform how we study the other planets. There's often a problem with space missions where space scientists, as a rule, tend to be kind of jacks of all trades, master of none. They might have one or two very special fields in which they drill down, but by necessity, they're kind of doing chemistry and physics, and they'll do astrobiology one day and they'll do geophysics the next, and so because of that, the knowledge is not so deep. So you get not about everything. I mean, there are things that they have very, very deep knowledge about. They're very good at modeling. You'll have geophysical modelers, you have chemists who are very good. Everybody does have their specialties, but when you have a geophysicist trying to talk about astrobiology, they might be out of their depth a little bit, and yet they often have to on a mission. And so we need then these missions go out and recruit from the Earth geology field to find people who can tell them about how paleo environments work, how preservation of materials work. For Curiosity, the project scientist went out and got a lot of science experts, people who are expert in evaluating whether very ancient Earth rocks contained life, people who are expert on those red beds from Australia that are 3.8 billion year old rocks. So Earth experts were invited to come speak to these geophysicists and geochemists and space remote sensing experts about how these materials get preserved in rocks and what you would be looking for with your rover in order to try to find evidence for past habitable environments. And so Earth benefits us in studying space, and then space benefits us in studying Earth, because in Mars, we get a planet that has all of the same physics and the same composition that Earth does, but it does not have either life or oceans to complicate things. So it's the geology, especially the active geology, is a lot simpler. We still don't understand what's going on, but there are a lot fewer factors involved. And so if we can explain something on Mars, then we can take that model and bring it back to Earth. And then, there you're adding back in life and oceans, and you can try to understand the complexity of the Earth that way. So there's a lot of interplay between the Earth sciences and the planetary sciences. And that's one of the greatest things about planetary science. Planetary scientists are very open with their data. They know how much they depend on other fields to understand what they're looking at. And so they're like, here, have the data, help us figure out what the heck's going on, because we sure have no idea. So it's fun. It's very international. It's very collaborative in that way.
That's excellent. Thank you. And just a little note, thing for myself, actually. I noticed in the pictures you showed around the sort of selfie of the rover, there was a drill hole sample, and it looked like there was fluid there. I was wondering if it was all dry drilling, or that was just a bit of fluid to clean the drill bit or something.
No, it's all dry. There are no fluids. In fact, there is a whole office at NASA called the Planetary Protection Office, whose job it is to make sure that a spacecraft like Curiosity that has not been sterilized to the very highest possible degree of sterilization, making sure that it never contacts anything liquid on Mars for fear of possibly contaminating it. In fact, there was a scare very close to launch on Curiosity, because as it was being prepared for launch, they installed the drill bit, and in so doing broke a seal. The drill bits had been sterilized to the very highest possible standard. And by I still have never gotten the full story about what happened, because I think nobody wants to claim fault for it. But basically, protocols that were expected by the Planetary Protection Office were not followed. This drill bit box that was supposed to be kept sterile through launch somehow. I'm not even sure how it was supposed to work, was opened while in a clean room in Florida in order to install the drill bit on the rover. And so the planetary protection officer had the power and even threatened to cancel the launch because they said, you have not satisfied our requirements and you could contaminate Mars. And so they had at the very last minute to get a letter from NASA stipulating that Curiosity could not touch anything that remotely looked like it had any chance of generating anything liquid. Because if it does, then it will fail its planetary protection requirements. It happens that because Curiosity landed so close to the equator, the environment close to the equator, it's actually quite warm during the summer especially. It gets up to like 20 degrees Celsius. And so water does not last around there. There's the rocks where Curiosity is are dry to a couple of meters depth, just because it actually bakes there. It's a baked vacuum in an oxidizing environment. It's super dry. So it's not a problem for them. It will be a problem for future missions.
Excellent. Thank you very much for that. Back over to you, Mark.
Well, thank you very much again, Emily. That was fantastic. I remember getting really excited as a child when the Viking landers landed there, and it's great that you've pulled all the exploration together over the next decade as well. So can we thank Emily once again for her talk? Really,
my pleasure. As you can tell, I love talking about this stuff.
You can tell it's really good. Thank you. Okay, that's it for us for tonight. Our next meeting is on the 3rd of June. It's a hybrid meeting, so you can visit us in person in Edinburgh or watch it on YouTube again if you're further away. And for our members, it's also our AGM. So